Hello everyone. In this video, we will talk about Shor's algorithm, which is an algorithm that relates finding the period of a certain function f to the prime factors of a number n. We start with a large number n, which equals the product of the two prime numbers p and q, and we can assume that p is greater than q. If n is even, we know q equals 2 and can easily determine p. When n is odd, we have to be a little bit more creative to find its factors and use a method such as Shor's algorithm. The central function in this algorithm is defined this way and is called the modular exponential function. C to the x is congruent to f sub n c of x modulo n, where c is a natural number relatively prime to n and takes values greater than 1 and less than n minus 1. Using this modular equation, we can see that f is the remainder in the relation. Starting at 0, as we increase the whole number variable x, f increases, but after a fixed interval, acquires the same values again. That makes f of x a periodic function. The idea in Shor's algorithm is to find that period r and use it to determine p and q. Let's look at the example where n equals 15. And let's choose c equals 7. We will evaluate the relation for x from 0 to 8 to determine the value of the modular exponential function in each case. For x equals 0, we get 1 is congruent to 1 modulo 15, so f of 0 equals 1. For x equals 1, we get 7 is congruent to 7 modulo 15, so f of 1 equals 7. For x equals 2, we get f of 2 equals 4. Similarly, for x equals 3, f of 3 equals 13. Then we get f of 4 equals 1. For the next one, we get this, then this, and so on. Observe how the value of the function changes. 1, then 7, then 4, then 13, then 1, then 7, then 4, then 13, then 1, and so on. From the first occurrence of 1 here to the next one here, there are 4 steps. So the period r equals 4. Notice how 4 also shows up here, where x equals 4. So in order to write an equation to relate r to n, we can focus on this equation. Let's write it using the general variables again. C to the r is congruent to 1 modulo n, which implies that c to the r minus 1 equals kn for some integer k. And using this relation, we can write the equation in this form. Let's write out n as p times q and call this expression a and this b. So we have ab equals kpq. Let's prime factorize the variables. Well, p and q are prime, so no need to do anything to them. But we need to write a, b, and k in terms of their primes. In the upper left corner is the way we represent them. For example, a equals a1 to the alpha 1 times a2 to the alpha 2, with the product going all the way to an to the alpha n. So expanding ab equals kpq, we get this. The product of a bunch of primes on one side and another product of primes on the other side. The fundamental theorem of arithmetic tells us that the prime factorization of any natural number is unique. So any number on one side has to correspond to another one on the other side. Let's focus on p and q. First scenario, p corresponds to one of the primes of a, let's call it ai, and q also corresponds to one of the primes of a, and let's call that aj. This means that n equals pq equals ai times aj. This also implies that the greatest common divisor of a and n is p times q, and that of b and n is 1. Scenario number 2. P is a prime of a, ai, and q a prime of b, bj. Here, n equals ai times bj, and its greatest common divisor with a is p, and with b is q. Similarly, when p is a prime of b and q of a, the greatest common divisor of n with a is q, and with b is p. And in the case when both P and Q are primes of B, then the GCD of A and N is 1, and of B and N is P times Q. Writing A and B out again in terms of C and R and organizing our findings in a table, we get this. Notice that calculating these two different GCDs yields the factors P and Q in 2 out of the 4 scenarios we discussed, the second and the third. When it doesn't, you don't have to give up. Just try a different C. Next, let's talk about a situation when we can get the factors directly from the definition of the function without having to resort to calculating GCDs. Recall this relation? When is k equal to 1? Easy. When c to the r minus 1 equals n. In that case, if we factor the left-hand side like before, we get this. So if p is larger than q, then this is p and this is q. You just read off their values, and all you need is to find r, which can be done with this period finding circuit, for example. It has multiple Hadamards, a gate that calculates the values of the modular exponential function in one step, the quantum Fourier transform gate, and a measurement on the argument register that reveals the value of r. As an exercise, recall the condition c to the r minus 1 equals n that guarantees finding p and q directly. For the n equals 15 case, find out what values of c satisfy this condition. Slán!